with many of the top powerful supercomputers. So, during the last 2 decades, we have seen a change in the high-performance computing world. So, what are the changes in the high-performance computing world? I will just point out those changes during my next few slides. Okay. So, in the last 40 years, we gradually changed our journey from the mainframe to cluster computing, then grid computing, then cloud computing. Okay, we started in 60s with mainframe computing computers, and our most compute-intensive programs were run on mainframe only. Then came the cluster. I'm not sure whether yesterday Dr. Sunirmal Khatua or Dr. Sharbani Roy, whether they discussed about cluster computing. I just give you a very brief overview. If we have a number of computers, say desktop computers, they are connected through, they work together without one particular job, then we can call it a cluster of computers. Cluster, when it is a cluster of computers, they are connected not with very fast interconnects like InfiniBand or something like that, but they can be connected using simple Ethernet LAN. Okay, so cluster computer, we call those cluster computing. In 1990s, I'm not going into the detail of grid computing now, because we moved from grid computing to cloud computing. If you ask me the details of the difference between grid computing, give an example. Grid computing means all of us have small resources, and we come together and decide we will take advantage of all our small resources. So we shall collaborate and then share our resources for doing a compute intensive job using all the resources. So that means we integrate our resources in such a manner that one of my job which cannot run my own desktop take advantage of all the desktop machines together and can be run efficiently. Similarly, I run my job for say tea time, and then you start your job after completion of my job. Then you can also use the computers to run your compute intensive program. So this is grid computing, where we all collaborate to run a particular computer program. On the other hand, cloud computing is not like that. Cloud computing, what is cloud computing? You listened carefully yesterday, I believe, but I just to complete my example, I just want to give one example. It is like a rich person, very rich person, having lot of resources. Okay, and whenever you request for any resource, the rich person will give you some portion of his or her resource on rent. Okay, so basically you rent some resource from, you don't need to install and maintain the large computers. What you do, you just request for some resource from the owner, and then the owner will, or maybe for molecular dynamics simulation, or simulation of the entire universe. So there were many such simulations, or maybe drug design, for which we required high performance computing. So previously, whoever required high performance computing needed access to one of those supercomputers. And you have seen how large are the supercomputers and how costly is maintenance and installation of such computers. But now we have cloud computing, and there are several companies who offer you cloud services, and you can just go for those. Okay, so this type of cloud access can be managed by many traditional as well as non-traditional HPC users. I will come to this traditional and non-traditional. So the examples are Amazon Web Service, AWS, Microsoft Azure, and probably you have heard about these names yesterday also. So they are HPC friendly public cloud for solving many of the HPC problems. And so far, actually, we have seen traditional HPC users who generally do weather forecast, who generally run weather forecasting programs or many such highly compute intensive programs were the HPC users. But now many non-traditional users also, because cloud is available on very low rent compared to supercomputers, therefore many non-traditional HP users also, they are availing the services from cloud for running their own program. Okay, they are also leveraging public cloud HPC solutions and running programs for machine learning and artificial intelligence challenges. Okay. And now actually cloud computing, I mean, this is 2016 data. Obviously, it has changed, and you see this figure. Here actually, again, I presume that yesterday you, I mean, not presume, I'm sure that yesterday you heard about infrastructure as a service, platform as a service, software as a service. So 3 types of service models for HPC users. Okay, so here I show the 2 graphs, 2 bar diagrams for 2016 and 2020. Now, if you a user of infrastructure as a service, perhaps you understood through, when you gone through your yesterday's lecture, that you need more knowledge on computer architecture, I mean, just processor, memory, as well as programming languages. Because in IaaS, you manage everything, okay? And in PaaS and SaaS, you don't manage everything. And particularly in SaaS, everything is managed by the cloud service provider or some other service providers. You are only user of those applications. Okay, so if you see in compared to 2017, in 2020, the IaaS, the percentage of IaaS use has reduced here. Okay, PaaS use increased because we are now using a lot of databases on top of, and many other applications. For example, here data organization and workshop management reduced, but clustering software and analytic tools, that increased. Similarly, professional services, those increased a lot. Okay, and managed services. So what I want to what I want to point out here is that gradually the dependence on cloud is increasing, and particularly for HPC users, dependence on cloud is increasing, but instead of using directly infrastructure as a service, users are more focusing on other levels of services. That means software as a service or PaaS, platform as a service, which means that instead of traditional HPC users, gradually non-traditional HPC users are more focusing and trying to solve HPC problems on top of cloud. Okay, so that is a change, but let us see what will happen gradually. So that means this is what the scientists, they call democratization of high performance computing, because now high performance computing is not a field for few scientists only. Now it is a field which is open to all. So if you want, whoever wants can move to high performance computing and work in this area. So again, this is another diagram where I have shown the, in fact, this is a diagram for worldwide public cloud services by segment from 2013 to 2017. This is, as you can see, these are the IaaS level increase. Okay, so there has been some increase at the IaaS level. PaaS also a little bit, but SaaS increased almost linearly. Okay, so that means again many users are now using the software level service on top. And cloud market revenue in billions of dollars. Here again, there had been little increase in PaaS, IaaS increased slightly, and SaaS increased a lot. Okay, so that means what the point which I want to make here is that non-traditional users, the users who do not have much knowledge about computer architecture, processor, memory, and cannot manage IaaS level resources, or even the platforms, that means the databases, etc. They are also now shifting their business or environment onto the cloud just to use the softwares on the cloud. And many of them are actually using high performance computing. So whatever I discussed, lots of data. We can see the social media data, sensor data, cell phones, GPS. We are purchasing over internet from Amazon, Flipkart, and whatever. We are ordering food from Swiggy and Zomato. Now, during this pandemic situation, we have even purchased groceries from Big Basket or many other companies like that. So all this data are sorry. Okay. Okay, thank you. So lot of purchases are over the internet, and then we browse. So www, World Wide Web. We send emails, media streaming. We watch cinema using Amazon Prime or Netflix or whatever. For healthcare, a lot of data is being generated, and IoT. Obviously, many of these are under IoT only. So now, what you can assume that lot of data are flowing over the internet, and obviously those data are being stored somewhere in some manner. Okay, even if you now just go through a website by Guardian, then also Guardian will store all your data, how you browse the web, whatever emails you say, everything will be stored. So a lot of data now actually they are saying that 90% of the data in the world was generated in the past 2 years. So you can think we are entering into a new age where we only have data and data and data everywhere. So the use of high performance computing is also gradually changing. How? Many of you perhaps listened about data parallelism and task parallelism, because here we have some faculty members, but still I'll just very briefly explain. So when we have, it is data parallelism is basically, it is a kind of a single instruction, multiple data sort of thing. That means whenever we have multiple data, say a loop working on different cells of matrix, like say matrix addition. So each cell of one matrix will be added with another cell of the second matrix. Okay, so the instruction is single add, but we have different data, right? So therefore that is we call it data parallelism. When we parallelize one such thing, that means each cell of two matrices, like A11 and B11 will be added by one processor. A12 and B12 will be added by another processor. A13, B13 will be added by another processor. That is what we call data parallelism. Okay, so divide the data in such a way that a single instruction will be run by every processor, but they will work on different sets of data. On the other hand, task parallelism is not like that. task parallelism means the entire program is divided into few tasks, okay, and each processor will run one particular task, okay. So here, this is an example of task parallelism. This is an example of data parallelism where in the first case we have one-dimensional. That means each of the rows are distributed among the processors. Whereas in this case, each row and each column, then this is a two-dimensional. So here each such column will be distributed among the processor. In this case, sorry, not row, the entire plane will be distributed among the processor. This plane and this plane, they will. Here each column will be distributed like this. So this is a two-dimensional one. On the other hand, three-dimensional means each cell will be distributed among the processor. So the instruction is one, but they will work on every such element. If you have, yesterday, I think Professor Sharbani talked about MapReduce. So MapReduce works on works in similar manner, data parallelism. Okay, we will come to MapReduce later. On the other hand, functional task level parallelism means divide the tasks among the processors. So here we have an example for the atmospheric model, the land surface model and ocean model can run simultaneously, and hydrology model can also run simultaneously. But obviously, we need some inputs from this. Some data transfer is required among these three models, and then all of them transfer the data to the atmospheric model, and then atmospheric model can run. So this way, the processors can divide the small functions among themselves, and they can work independendly, and sometimes they need to transmit messages among themselves, but that can be done parallel execution and then transmit messages, parallel execution and then transmit messages in this manner. Okay, so this is what we call task parallelism. So in the 1970s, we mainly focused on data parallelism, and that time we had many computers like vector processors, array processors, which mainly focused on data parallel paradigm. Okay, in 90s we mostly focus on Momita. Yes, Momita. That's right. Task parallelism means you can say MIMD. Okay, so that's true. Just 1 minute. One minute, please. So, task parallelism, you can say it is comparable with MIMD, but obviously SIMD and MIMD, these are the taxonomy which we invented in 1970s. But after that, the computer architecture evolved a lot. Okay, so now we mainly talk about in terms of data parallelism, task parallelism, and also sometimes we make a hybrid of these two model. And so gradually we are now focusing on hybrid model and off-the-shelf computers. Okay, so that is why we work with clusters. So with big data applications, opportunity for exploiting data parallelism increased, because now you have a lot of data. You are generating trillions and trillions of data every year. So therefore, you have more opportunity of exploiting data parallelism instead of task parallelism. And in fact, most of the artificial intelligence programs now, machine learning programs now, are designed to exploit data parallelism. The third change in this field is rise of GPU computing. In fact, earlier we used to use GPU, graphics processing units, only for graphics purposes. We never thought about that we never thought that, okay, we will use GPU for some other purposes. In fact, gradually when superscalar architecture evolved in 90s, then we have started seeing that within a processor, we have multiple integer units and multiple floating point units. That means earlier, just one processor could carry out one integer calculation or one floating point calculation at a time. I mean, either one integer calculation or one floating point computation at a time. But when superscalar architecture grew, then actually we found there could be multiple integer units, multiple floating point units, and these units can work parallelly. And that is why instruction level parallelism came into the picture. But that means even an instruction, one arithmetic expression, say A plus B plus C plus D, can actually divide it into two components. One instruction unit, integer unit can compute A plus B, another integer unit can compute C plus D, and then both can be added by another integer unit. So this way actually we used to exploit integer level parallelism in all the computers. Even your mobile phones and your laptops now have integer level parallelisms within their processors. But then the scientists started thinking that why don't we have GPUs to work for such type of parallelism? So GPU computing started improving. And you will be surprised to know, I have just given one example here. Every year, a top 500 supercomputers list is published by one organization. The organization is also the top 500 supercomputer organization. So they publish a list of top 500 supercomputer list, okay, ranking list. And you will be surprised to know in 2019, this top 500 supercomputer ranking list includes 136 GPU accelerated supercomputers. And NVIDIA is the company who first brought GPU into high performance computing market. That means NVIDIA first thought that, okay, we can use GPU for parallel processing. So they first introduced GPU for high performance computing, and these supercomputers, they included GPUs. So whatever you have seen, the processors, the boxes which we have seen earlier, many of those boxes contains nodes which are combination of CPUs as well as GPUs. Okay, 40% of the total compute power on the top 500 list comes from GPU accelerated systems. So you can think that how useful are the GPUs nowadays. This is one example. The second most powerful supercomputer that contains 4,356 nodes. Each node is equipped with 22 core power 9 CPUs. So each node has 2 CPUs. Each CPU has 22 core. You can multiply. Okay. And each node has 6 NVIDIA Tesla V100 GPUs. This is the brand name, but they have 6 GPUs. So now you can multiply 4,356 into 2 into 22 into 6 GPUs. GPUs also has many cores. I will come to that. So you can think about number of cores inside one such node. Okay. We only talk about quad core and 8 core and something like that. IBM built this one. This IBM built supercomputer, the second most powerful supercomputer that delivers 148.8 petaflops. Flops, if you do not know, just flop is what? Sorry, what was the question? I will come to this. What are the advantages? Then multiple CPU. Yes, I will come to this. Sure. In fact, next part, in my next part, I will mainly discuss on this particular. I will mainly focus on this only. Okay. So you can now think about these machines. A simple laptop, what you often use. Okay. So display, I have just added the configuration just to make you interested. But you all, many of you know, particularly the students, they now look for uh, computers with GPUs. So display is only 15-inch, storage 500. These are general, but with a processor, Intel Core quad core, you have NVIDIA GTX 1050 4GB, where we have 768 CUDA cores. Operating system Windows, but obviously you can have other operating systems also, Linux, Apple, Mac, whatever you require. What is the advantage? In fact, I will come next, but give me some more time. Let me finish with the 5 trends, and then I will come to that. What is the advantage? So GPU, in fact, this graph will show you some advantage. So here, this shows the milliseconds, execution time in milliseconds. So the first one, the magic U, and